Good morning and welcome to the 40th lecture of the course Water Resource Systems, Modeling Techniques and Analysis. Over the last few lectures, we have been now discussing model formulations for specific problems. For example, we started with the conjunctive use of surface and groundwater. Then we went on to look at the hydropower optimization. And in the previous lecture, I discussed crop yield optimization, which especially is useful in the problems relating to irrigation scheduling, where we would like to allocate a given amount of water in different time periods and specifically to a number of crops, all of which are competing for the same amount of resource. So, in the last lecture, what we did was that we looked at the crop production functions. For example, you may have a multiplicative production function, you may have an additive production function. Typically, they relate the actual evapotranspiration to potential evapotranspiration ratio to the actual yield to the maximum yield ratio. Here also AET is the actual evapotranspiration, PET is the potential evapotranspiration, and typically these production functions are defined for the deficit evapotranspiration. For example, 1 minus AET by PET, here also 1 minus AET by PET. ETA and AET are the same, actual evapotranspiration for crop C here and potential evapotranspiration for crop C. So, when you write for a single crop, we look at AET by PET for the growth stage G, and here also we are looking at the growth stage S for the crop C. So, this is for crop C. We specifically discussed the soil moisture balance from time period T to time period T plus 1, and typically, as I said, these periods can be of daily interval, but in many cases we aggregate the soil moisture, lump it over a period of 10 days. So, this can be 10-day period. So, starting with the given soil moisture, we know how to obtain the end of the period soil moisture. Starting with the given soil moisture at the beginning of the time period T, we know how to obtain the soil moisture at the end of the time period T, which is also beginning of time period T plus 1. We add the rainfall and the irrigation allocation, we take out the evapotranspiration, we take out the deep percolation if any, and we also account for the soil moisture in this additional soil layer that gets added from period to period. So, we are accounting for the increasing root depth across time here when we are doing the soil moisture. In obtaining the actual evapotranspiration, we have used a relationship like this, which depends on the available soil moisture, that is the actual evapotranspiration to potential evapotranspiration ratio depends on the available soil moisture. By available soil moisture, I mean the soil moisture minus the wilting point. So, the maximum available soil moisture will correspond to the actual soil moisture being at field capacity, and there is a depletion that is allowed. By that I mean the soil moisture can go down up to certain point without affecting the actual evapotranspiration being equal to potential evapotranspiration. So, in this range AET is still equal to PET. Beyond this range, the AET starts decreasing, and then at available soil moisture equal to 0, which happens when the actual soil moisture is at wilting point, the AET becomes 0, and that is a condition that we put in optimization. So, looking at all of these together, we formulated in the previous class a linear programming problem through which we obtain optimal allocations. First, we considered a problem of a single crop, and we are looking at optimal allocations of a given amount of water for the entire season, the allocations in intra-seasonal time periods. This was the first optimization problem that we looked at. Then subsequently, we extended this to multiple crops, and then for every time period the water available is known, you are distributing the amount of water known to be available at the beginning of every time period, intra-seasonal time period across the crops. Then towards the end of the last lecture, I also mentioned that you can link this problem with the reservoir operation itself. So, that every time period what should be the water available can be decided in that integrated optimization problem. Now, in today's lecture, what we will do is we will look at large systems, essentially large water resource systems. For example, several basins, several river basins, and then you are linking from one basin to another basin, you are transferring water. Such huge systems, how do we analyze? And then subsequently, we will also look at one river basin, but with a large number of reservoirs. How do we operate or how do we analyze such large water resource systems is the focus of today's lecture. The systems techniques, in fact, are useful for what are called as screening of alternatives. What is called as screening of alternatives? When you have huge systems, let us say that you have a large river basin such as Narmada, such as Krishna, Mahanadi, etc., where or even the Damodar Valley Corporation, where you have from 5 to 14, 15 reservoirs, some of them are medium, some of them are large reservoirs. We need to look at these systems as one integrated system and then analyze these systems. When we are doing that, we run several simulation models built, that is we run a simulation model several times and generate large number of alternatives, which will provide questions to what if such a situation occurs, how does the system perform. That is, these are the type of questions that we will be interested in answering. So, what we will do now is, we will take an interbasin transfer system, which is in fact a proposed transfer system in India, and this analysis is meant for academic purposes to demonstrate how such large systems can be analyzed. We build the system simulation model and then look at optimal availability of water across the different basins. So, let us understand these type of systems now. So, as an example, we will take this proposed interlinking scheme, where you have 4 river basins, Godavari, Krishna, Pennar and Kaveri. Now, these are the 4 river basins that we have, and there are a large number of reservoirs. Some of them may be proposed reservoirs, some of them may be existing reservoirs. So, here the continuous line triangles here indicate existing reservoirs, the dotted line triangles indicate proposed reservoirs. So, you have, for example, you have the Nizam Sagar here, Sri Ram Sagar here on the Godavari, Ichampalli which is proposed, Polavaram which is proposed. Then on the Krishna, you have the Tungabhadra coming from a tributary. Then you have Sri Shailam here, Nagarjun Sagar, then Prakasham Barrage, Pulichintala reservoir which is proposed. Then Mailavaram on Pennar, you have Mailavaram and Somashila. Then on the Kaveri, you have Krishnaraj Sagar, Mettur and Upper Ranikat. Now, this is a large system. We are talking about 4 major river basins. The numbers here within the triangles indicate the storage in 10 to the power 6 meter cube, that is million cubic meters. So, these are the storage capacities that are available. For each of these basins, the total catchment is also given here. So, as you can make out from this system along with the numbers that are available, you can see that it is a major system, it is a huge system in fact. Now, when you are considering such systems, okay, we will also see some other facts here. These links that are shown here, these dotted with arrow links, these are the proposed linking for the basins, that is Godavari is proposed to be linked to Krishna through this link, at 3 points. One is from Sriram Sagar to Srishailam, then from Srishailam to Mailavaram, then here from Ichampalli to Nagarjuna Sagar, then Nagarjuna Sagar to Somshila. Like this, there are several links that are proposed. When you are analyzing systems like this, you would like to place priorities. First of all, we need to build a simulation model which will reproduce the behavior of such a complex system. As you can see, whatever action that you take here is likely to affect the storage at this point, and therefore, that will affect the transfer performance. It will likely to affect the downstream reservoir and so on. Similarly, if you are linking these two, the actions that you take at any point upstream of that is likely to affect all of the downstream points. Suppose you make a transfer here. Now, that transfer can be put into use here, or that transfer can be put into use here, or can be all the way taken back up to this point, upper Anicut. Similarly, transfer that you make here can be taken for use here or for use here, etc. So, any action that you take at a point is likely to affect several of the downstream points, and you are looking at huge amounts, huge quantities of water, both at the reservoirs as well as at the linking points, as well as at the links. So, how do we simulate this? When you want to simulate at any given reservoir, first of all, the reservoir is serving for its own purposes. It may have a hydropower generation, it may have a irrigation demand, it may have drinking and municipal water demand, or it may be protecting against floods. Therefore, it has to protect, it must have flood storage and so on. So, at each reservoir now, we will say that first priority is for it to meet its own requirement. So, this reservoir, for example, Sriram Sagar has been built for a certain purpose. First priority is to meet all of its purposes. It has to meet its own irrigation demands, it has to meet its own water supply demands in terms of municipal and industrial water supply. It has to meet, if at all there is hydropower, it has to meet its own hydropower demand. It has to account for the flood control if it is meant for flood control and so on. So, first it will meet all of its own requirement. Then it will look at this particular reservoir, we will see what is happening to the downstream reservoir of the same basin. So, if a downstream reservoir of the same basin is in deficit, then if this reservoir is in excess, we will meet the demands of that particular basin through this. Remember here, when I am saying you meet this demand from this reservoir, it is not for individual time periods. Not every time period, every 10 daily time period you supply from here and so on. You have to simulate this system and run the simulation model over a large number of times and then arrive at certain policies. Now, in arriving at such policies, you need to define the priorities. So, the first priority, as I said, is to meet its own requirements. Then you look at the downstream reservoirs for that particular reservoir and see whether you can meet the demands of the downstream reservoir if it is in a deficit. The third priority will be to look at other basins. So, from the Godavari basin, if we are looking at Sriram Sagar, first we meet all its own demands. Then, if we are still in excess, we meet the demands for the downstream reservoir for the same basin, Godavari. If after meeting the downstream demand, if we are still left with water, then we start looking at other basins, whether we can transfer the water to other basins. I repeat, this should not be done from period to period. That is, for every time period, we should not apply this policy. But overall, when we operate this system for a long period of time, the simulation model should simulate on an annual scale. For example, annually what is the kind of transfer that is possible, annually what is the kind of deficit that is possible. In large systems, the time frame of analysis also should be large. You may typically look at 50-year sequence, 100-year sequence, etc. So, you simulate these kind of systems over a fairly long period of time and then look at whether such transfers are feasible, whether such transfers are reliable, whether such transfers can be used to increase the irrigation potential, can be used to increase the water supply potential, and so on. So, these systems, because they are spatially large, you must analyze over a fairly long time horizon also. So, typically we take 50 years, 60 years, 70 year sequences and not one sequence, we analyze these for several such sequences. So, we will see now how we formulate such a problem. The first level exercise is to build a good simulation model, which means what? We will have the inflow sequences at all of these, that is the natural inflow sequences we will have at all of these reservoirs. Then we may start looking from the downstream most reservoir or from the upstream most reservoir. For example, we may start looking at the downstream most reservoir of a particular river basin. You know the flows that are coming there. Then you start meeting the demands. If there is a deficit, you go upstream and then check whether you can meet the demands from the upstream reservoir. And then one by one you keep moving in a certain direction, either you go from downstream to upstream or upstream to downstream. Why I say either direction is because you are running the simulation model several times. It does not matter whether you start from the downstream most and go upstream or upstream most and go downstream, as long as your algorithm is correctly written for that particular direction. And then we exhaust all of these transfers and releases, meeting the demands and all of these for a given sequence of inflows. That is how you build the simulation model. Knowing the demands at each of these reservoirs, knowing the capacities of the transfer links, knowing the inflows and knowing all the salient features at all of these reservoirs. So, what do I mean by salient features? We have dealt with earlier the features such as the area capacity relationship, storage elevation relationship and the hydropower the constraints or the hydropower features that you have at each of these reservoirs, the type of canal systems that exist, the type of irrigation demands from one time period to another time period, the type of cropping pattern and so on. So, all of these are known at each of these locations. Then we are trying to see how we simulate this system. By simulation, I mean how do we reproduce the behavior of the system for a given set of inputs and for a given set of demands. So, that is what we will look at now. And these are the features. For example, this is Nizam Sagar, this is Sardar, this is SRSP is Sri Ram Sagar, then Echampalli, Polavaram, Tungabhadra, etc. All of these features are known. There is a power generated at certain places. For example, Echampalli you have a 975 megawatts and 770 at Sri Shailam and so on. So, all of these are the features, dead storage, live storage and command area is known, catchment area is known, then the period of inflow record is given here. So, there is a fairly large period of record. I would like to emphasize here that this study is a fairly old study and therefore, we have stopped around 1987, but the same thing can be taken forward if more recent data is available. The idea here is not to consider the case study, but to indicate how such large systems are analyzed. Now, as I said, we will have priorities at individual reservoirs. So, individual reservoirs have to meet their own demands. Then after meeting their own demands, you look at, when you are at a particular reservoir, you look at the downstream reservoirs of the same basin. Then if you satisfy the demands from this particular reservoir, what I mean is, let us say you are standing here at this point in the simulation. In the simulation, you are moving in certain direction and have come to this reservoir. You first satisfy its own demands, then look at the demands of the downstream reservoirs and satisfy the downstream reservoir demands. If you still have excess water, then you look at the other basin to which a link exists. If there is no link, then you do not look at, but if there is a link exists, then you look at the other river basin. This type of analysis we do by converting the storage or by dividing the storage into various zones. We may say that if the storage is in a particular zone, then you meet certain type of releases. For example, you may say that after meeting its own demands, first priority is to meet its own demands. Until you meet the demands of a particular reservoir, you do not even consider release for the downstream reservoir or transfer to the other basins. First meet its own demands. After meeting the demands, if the storage is above a certain minimum level, I call it as SREL. So, after meeting its own demands, if the storage is above this particular level, then you make a release to the downstream reservoir. So, SREL is the storage capacity above which release to downstream reservoir is possible, but no transfer yet. So, you are in this zone, you only make release to downstream reservoir, do not make any transfer. Then you have met the demands of its own of the particular reservoir, then you have also made the release for the downstream reservoirs, and you are crossing certain other zone. This is STRA. STRA is the storage capacity above which both release and transfer are possible. So, which means you make the release, you make its own diversion for the demand, and still you are above this, then your transfer to other reservoir is possible. Now, the question is, what should be these levels now? STRA, SREL, what should be these levels is the question. The MDDL, which is the minimum drawdown level, is known. The S max, which is the maximum capacity, maximum live storage capacity from MDDL, that is known. So, these two are fixed. We need to look at what should be the optimal SREL and what should be the optimal STRA, such that this large system becomes reliable in terms of its ability to meet the demands at all the locations. And subsequently, if we are able to meet the demands, we will start looking at, can we increase the irrigation potential, and therefore, can we increase the utilization value of the water itself. That is, from one basin to another basin to another basin, you are looking at increasing the value of the water. For example, if you are looking at the downstream most point in the Kaveri basin, if you have deficit at these locations, and if through such transfer links you are able to meet the demands first, and then can we increase the irrigation potential at these points, because you can have excess water from these points. So, these are the two questions that we will answer. In answering those, as I said, you need to look at the zones, storage zones, and then ask the question, what should be my optimal SREL, which is the storage zone above which release to downstream reservoir is made, and STRA, storage zone above which you make the release for the transfers to other basins. That is the idea now, and this we need to do for each of the reservoirs. So, these values will be different for each of the reservoirs obviously. We will now define the release and the transfer policies. First, meeting its own demand, there is no policy. If water is available, simply meet the demand. There is no policy, that is a standard operating policy. You look at any particular time period, if there is a certain demand and you have water to meet that demand at that particular reservoir, simply meet it. Do not look at other reservoirs, do not look at other time periods, do not look at other basins. That is a diversion policy. Then we look at the release policy. That means, you have met the demand at a particular reservoir, but still you have water in excess of SREL. SREL is the storage zone for release to be made to the downstream reservoirs of the same basin. So, that is the release policy. Look at this now. What we are saying there is from a particular reservoir M to a downstream reservoir L of the same basin. Here when I say this is release is for the same basin. So, what we are looking at is we are standing at a particular reservoir M and we are saying a release to be made to reservoir L. First of all, this storage that is available here in reservoir M must be greater than that particular zone here. So, we should be in this zone. So, storage must be greater than SREL after meeting its own demand. So, I will define S1T here for the reservoir M, that is in the time period T, as the storage at reservoir M during period T after accounting for its own demand DTM, that is in time period T at reservoir M. So, meet all of its own demands, then releases and transfers committed to the reservoir M from other reservoirs. So, you may have transfers coming from other reservoir of other basin, you may have release coming from its own other upstream reservoirs from the same basin. You account for all of this input that has come here and then call it as S1T. So, S1T is the amount of water that is available after you meet the demand and after you account for all of this. And if this S1T is greater than SREL, that means you are here now after accounting for all those various variables, you are here now storage. Then you make the release to downstream reservoir L. How much do you make? You make a release of whatever is in excess here or whatever is demanded at this point. So, you take the minimum of what is available here or what is deficit at this point. At the storage L now, what is the deficit? DTL is its demand and STL is its storage after accounting for whatever you have got from there. So, this is the deficit there, and this deficit you have to meet from this particular reservoir. So, you may make a minimum release from reservoir M to reservoir L to meet its own demands or whatever excess water that is available, out of that whichever is the minimum. And this 0 otherwise means that if neither you are in that zone or there is no deficit here, then you do not have to make any release, you do not make any release in fact. So, that is the idea. Now, when we reckon the deficit at the reservoir L, downstream reservoir L, you would have accounted for whatever transfers and whatever releases that it would have got. It may have also got some transfers here and it may have got some release from other reservoirs upstream of that, but downstream of M. So, you may have several other reservoirs here. So, all of these you account for and then make a make the release. I will repeat that. That is the, we are talking about the release policy. We are asking for how much to be released from M to the reservoir L to meet the demand deficit, which is dt minus st at reservoir L, and this STL should account for whatever transfers that the reservoir L has got and whatever release is from other reservoirs that it has got. By release, I mean the amount of water released to meet the requirement of the downstream reservoir. So, that is what we look at. So, that is what this says. And if there is no deficit here, you do not make any release from reservoir M to reservoir L. Much the same way, we talk about Alright, there is one more small issue here. We said this SREL and STRA are the storage zones. They determine the storage zones within which release and transfer is possible. So, in this zone release is possible. By release I mean the amount of water released for downstream requirement, that is the requirement of the downstream reservoir, and this is the transfer zone. If you are above STRA, you make the transfer. Now, these zones are typically defined for season, that is you do not change these zones every time period. If you are talking about 10-day time period, you do not say that during this 10-day time period my zones are like this, during the next 10-day time period these zones are like this, etc. Typically, these zones are defined for monsoon season and non-monsoon season, or you may also have it for annual season, annual time periods. Simply have one zoning for the entire year. So, these zones in this particular example that I am showing are defined for the season J. So, whenever I am talking about SREL and STRA, we talk about the season J. Much the same way we do the transfer. So, the amount of transfer that we are looking at, by release I mean the release for the downstream reservoirs, by transfer I mean transfer for the reservoirs in the other basin. So, whenever I use the word transfer, it is from one basin to another basin. When I use the word release, it is from one reservoir to another reservoir, downstream reservoir for the same basin. So, the transfer that is made in time period T from the reservoir M to the reservoir P is what we are looking at. So, this is one basin, this is another basin. Now, this is one reservoir M and this is a reservoir P here. These two are different basins and there is a link that exists. So, we are talking about the transfer from reservoir M to reservoir P. Now, this transfer now, we are now introducing S2T at M. So, S2Tm is the storage available at reservoir M after accounting for the diversion. By diversion I mean meeting its own demands, and release. Release is the release for the downstream reservoirs of the same basin. So, we have met its own demands, we have met the demands for the downstream reservoirs L, and still we are in excess of water, then we look at the transfer. So, that is the amount of transfer. It is exactly same as the release policy, except that we are looking at the storage S2T now, and we are looking at two reservoirs in two different basins. So, this is one basin, this is another basin. So, that is how we decide the amount of transfer from one reservoir to another reservoir, from reservoir M in one basin to reservoir P in another basin. Then at every reservoir you will have storage continuity, you will have its own constraints and so on. So, all of these are typical multi-reservoir system simulation which I have discussed earlier. So, at every reservoir you meet the storage continuity equations and then you put on top of all of them the release policy as well as the transfer policy, and then you simulate the system. So, this is the transfer policy and then we will do, as I said, when you are able to meet the water demand at each of the reservoirs by accounting for releases, by accounting for storages and so on. When you do this, if you see that all the demands are met, all the existing demands are met, then you start looking at, can we increase the demands? What I mean by that is, can we increase the irrigation potential? Can we increase the hydropower potential? Can we increase the municipal and industrial supply potential? So, once we are able to meet all the demands, then we start looking at to what extent we can increase the irrigation potential, to what extent we can increase the hydropower potential, etc. So, we start multiplying the demands and then start looking at how best the water can be utilized, and that is where we put two factors, INCR and 1 and INCR 2 for the two seasons, monsoon season and non-monsoon season, to see in monsoon season whether we can increase and by what extent we can increase, and in non-monsoon season to what extent we can increase. So, like this we do the simulation, and the type of analysis that we get, we do a 50-year simulation. This is just a summary. It shows now here from one point to another point what is the kind of transfer that has taken place. So, the first figure here shows the transfer from Echampally to Nizam, that is NS is Nizam Sagar. So, that is the transfer that is possible from Echampally to Nagarjuna Sagar, I am sorry, from Echampally to Nagarjuna Sagar. So, this is the type of link that we have here. So, we can make the transfer from Echampally to Nagarjuna Sagar, and that is the type of transfer that we get from one point to another point. Similarly, Echampally to Prakasham Barrage, Echampally to Puruchintala and so on. So, Polavaram to Prakasham Barrage, Polavaram to Mailavaram and so on. Now, it need not be direct link, but it can be an indirect link. What I mean by that is, you may have a link from here Echampally to Nagarjuna Sagar, and from Nagarjuna Sagar you may have a link to Somachila. So, you can talk about from here to here or from here to here. Similarly, when you are from Sriram Sagar, you can come to Srishailam, then to Mailavaram, then to Somachila. So, the transfer, if you have excess water here, you can take it all the way up to Upper Anicut. So, we can show this as Sriram Sagar to through Srishailam to Mailavaram to Upper Anicut. So, that is a way we analyze the system, and these are the numbers that we have got for a 150-year simulation. What do I mean by 150-year simulation? We may have several such sequences. I will talk about this in subsequent example, where we generate not one sequence, but we use several such sequences and do several such analysis to obtain what kind of transfers that are possible and how many times in 50-year sequence, how many years the transfer has been possible. For example, here 43 times it is possible from Polavaram to Prakasham Barrage and so on. So, this is the type of numbers that you get. Remember, these are planning models where you look at an overall picture, both with respect to space as well as with respect to time. Over a 50-year time periods, how many times we could make the transfer, and what is the total transfer in the 50-year time period from one basin to another basin and so on. Then we ask the question. Now, this we did with a fixed SREL and STRA. What we are doing there is that these zones that I showed, SREL as well as STRA, we start with a particular SREL and particular STRA at each of the reservoirs. We know this level, we know this level, and then we start with a given or pre-specified SREL and pre-specified STRA, make the simulation, look at how well the demands have been met, change SREL, change STRA, again do the simulation, again look at how well the demands are met and so on. So, like this you can keep running the simulation model several times, but obviously because the system is large and you will have SREL, STRA at each of these, and to such, because you are talking about monsoon period and non-monsoon period. So, at each of them you have to deal with 4 variables, SREL1, SREL2 for monsoon and non-monsoon, STRA1, STRA2 for monsoon and non-monsoon at each of these reservoirs. And therefore, doing it manually, that means manually every time you change the SREL and then go to the next simulation run at each of these reservoirs. It becomes not only cumbersome, not only unwieldy, but also extremely subjective. So, finally, you do not have trust on the optimal results that you get. And therefore, what we do is the simulation model that we have built, thus we put it into a more formal optimization algorithm. So, there is a simulation that we have put, this is the simulation model. Now, this simulation model apart from all other inputs will take inputs as SREL as well as STRA at each reservoir, and that is the type of results that you get for a pre-specified SREL and STRA. We now build this whole system into an optimization problem in which these SREL and STRA are varied systematically. So, you may have a nonlinear search algorithm in which, depending on the type of system performance measure which we will define as this, depending on the system performance measure, it will adjust the values of SREL and STRA at each of the reservoirs. So, you have a simulation model, superimpose on it an optimization model. The optimization model will give you the optimal SREL and STRA by making search over all possible values of SREL as well as STRA at each of the reservoirs, such that you are able to meet a certain objective. And the objective function here we consider for that is, now how we solve is slightly beyond the scope of this course, but you realize that we use a nonlinear search algorithm. You can in fact use algorithms such as genetic algorithm or ant colony optimization and so on. It is in such situations where you have to have a large simulation and then on the simulation you need to do an optimization. In such situations, the evolutionary algorithms such as the particle swarm optimization, genetic algorithms, the ant colony optimization, etc., these can be used here. Now, in this particular example that I am showing, we use a simple nonlinear search method which is available in many of the standard scientific programs such as MATLAB. Now, we look at what is the objective function here. We are saying at a given reservoir K for a time period T, we are saying the utilization of water in that reservoir for that time period, we are calling it as U, and the utilization is the amount of water that is used for meeting its own demand plus the amount of water that the reservoir K has released to meet the demands downstream, that is at the downstream reservoir, plus the amount of water that the reservoir K has transferred to other basin. All of these three together we call it as utilization. So, the amount of water that was available has been actually utilized, and that is the term UTK, that is what I am saying here. Then there may be deficit at the reservoir K. So, DTK is the deficit in reservoir. Obviously, these two together cannot occur. I am sorry, I will repeat that. UTK, if it consists of release and transfer terms, then DTK cannot occur, because DTK would be first met out of the UTK. So, DTK is the deficit from its own demand. That means, the water was not sufficient to meet its own demand in reservoir K in time period T, that is the deficit, and we associate values alpha and beta. These are constants. These can be economic returns or economic value attached to the water that is utilized, alpha, and the economic loss that is attached to deficit, but these can be weightage factors. We can look at it as a multi-objective problem and then assign weights and play around with the weights to get different solutions. Then we have the diversion policy, that is to meet its own demand. Now, its own means at the reservoir K. This is just the standard operating policy. That means, you look at the water that is available. If it is greater than the demand, you meet all the demand. If it is not greater than demand, then you bring down the reservoir storage to 0. That means, you release all of the amount of water available SITK plus ITK for meeting the complete demand DTK. Okay, now in addition you will have the release policy. I am writing the optimization problem now. We have written the objective function, we have written the diversion policy. Similarly, we write the release policy. Release policy is the same as what we put there. This is a release policy, and similarly the transfer policy. So, these become constraints. So, release policy is one set of constraints, the transfer policy is another set of constraints, and then you have the storage continuity equation, physical constraints, for example, the canal capacities, the hydropower installed capacity, the storage being limited to the minimum storage and the maximum storage, etc. All the physical constraints you will have, and then non-negativity of variables, and also then we may have constraints due to priorities. That means, we will have to say that first you meet its own demand, only then you consider the release, only then you consider the transfer, which are put in terms of the release policy as well as the transfer policy. Then we have the definition constraint. For example, you look at UTK, this is the utilization. The utilization at reservoir K in time period T is first its own demand, diversion is for its own demand, then release for meeting the downstream demand, that is demand at the downstream reservoir, then this is the transfer. Similarly, this defines the deficit DTK, that is demand minus the utilization. As I said, if there is a release and transfer, or if there is a release, then UTK will be consisting of, that is the demand will be completely met, because diversion K will be equal to the demand K, and therefore, it will be 0 otherwise. So, that is a definition for DTK, deficit, and the small DTK, which is the demand, we will now put it as the specified demands. DMTK is the specified demands. We will multiply to see whether we can increase the demands at the reservoir K. So, that is the factors. Now, these factors also come out as decision variables when we solve the problem. That is, at each reservoir, remember they are not changing with respect to time. At each reservoir, simply we are saying that by how much factor, by what factor we can increase the irrigation demands. That is a question that we are asking. Then all the physical conditions, etc. So, the simulation model that we had built earlier, we will now formally put it as an optimization problem, where there is a search over all these variables, decision variables, STRA1, STRA2, SREL1, SREL2 at all of these reservoirs, and INCR1, INCR2 at all of these reservoirs. So, the nonlinear programming makes a systematic search and then finally gives you the optimal solution in terms of what are the SREL1, SREL2 at each of these reservoirs. Now, 1, 3, 1, 4 etc. indicate the basin number and the reservoir number. So, the basin number 1 is Godavari and reservoir number 3, 1 and 4, 2 and 3, 2 and 4 like this. So, for all of these you get the storage zones. Now, for example, 1, 4, if you look at 1, 4, these notations are for 1 is the reservoir, 1 is the basin and 4 is the reservoir. So, this is Polavaram is 1, 4. Now, if you do not have anything downstream, that is there is no downstream demand, then obviously release term will be 0, whereas transfer term may be possible. So, you may not have a release zone, but you may have a transfer zone. So, that is how you put the optimal results here. So, finally, what you get out of the optimal solution is that you are making the transfer zone as well as release zone for both monsoon as well as non-monsoon periods. So, this is we are saying at the reservoir 1, 3, the SREL2 will be 2793 million cubic meter, which means only when you cross this storage, you start releasing. Similarly, if you cross this storage 3873 million cubic meters, then you consider the transfer. So, by doing this optimization, what we have achieved is at each of these reservoirs, we are defining the zones. So, the optimal zones, optimal storage zones is what we get out of this. Then we ask the question, how good are the solutions? If we meet all of these, it has maximized some objective function, and therefore, it has done some nonlinear search and finally provided us with the optimal storage zones at each of the reservoirs. But how does the system perform if we use these kind of storages over a long period of time, is the question that we need to answer now. Now, to answer that, we evolve several performance criteria. First level question is that at each of the reservoir, has it been able to meet the demands? We do all of these optimal storage zones and then operate according to the policy, the release policy, transfer policy, the diversion policy, etc. We do that at each of the reservoirs in such a complex system. So, how does this system now perform with respect to these optimal storage zones is the question that we need to ask. To do that, we evolve performance criteria, and the first level question that we ask is, how reliable is the system in terms of its ability to meet the demands at each of the reservoirs and the system as a whole. The system as a whole has certain demands. Has it been able to meet those demands? Then in the periods in which it was unable to meet the demand at a particular reservoir, it has gone into failure state. How long does it stay in the failure state? How quickly can it recover from failure? That is a resiliency. Then what is the effect of the failure itself? There was a deficit, but this deficit may have occurred at a very critical time, and therefore, the effect of the failure can be very large. Or there was a deficit, but it occurred in such a period that it did not matter much in terms of the performance of the system. So, what is the vulnerability or the effect of the failure itself, and what is the deficit ratio? How many times the reservoir levels went down, went below a certain threshold value, and so on. So, these are the types of performance measures that we formulate. There are large number of such performance measures. We will take 4 of them. In fact, 5 we will take. First is the failure index. Simply take the ratio of the sum of all the failures. Now, failures we may define variously. We will simply say that inability to meet the demand is a failure. Now, this can be aggregated demand, or it can be separately for irrigation demand, hydropower demand, and so on. Then we will call it as reliability, that is 1 minus f, which is the ability to meet the demands. Then resiliency, as I said, is the ability of the system to recover from a failure. This we compute as ratio of the number of transitions from failure state to a satisfactory state divided by the total number of failures. This is how we calculate resiliency. Similarly, vulnerability. In this particular problem, we define it as the largest deficit that has occurred divided by the corresponding demand, and deficit ratio as ratio of the total deficit to the total demand. Like this, we define different performance measures and look at how the performance of the system has been. So, yearly performance of the entire system looks something like this. We would like to have a system with a high reliability as well as with a high resiliency, but low vulnerability and low deficit ratio. In this particular case, the vulnerability is still quite large, indicating that if a failure occurs, the effect of the failure can be quite large. Similarly, we determine it for the monthly performance. Then at each of the reservoirs, we look at each of these reservoirs how the system has performed. So, this is the use of the simulation model in the case of large systems. So, in the large systems, first we build the simulation model and then put it into an optimization model, and look at how do we operate these large systems and how do we define storage zones at each of these reservoirs such that the system performs in a satisfactory manner. And these are systems analysis model. Remember, you do not apply these directly onto the field. These are systems analysis models by which you can judge whether it is the transfers are possible, to the extent transfers are possible, and so on. So, that in essence what I wanted to cover in this course, but these are preliminary techniques that we have learned for a new student. Essentially, we have learnt in this course the techniques of systems analysis, starting with the classical optimization techniques, the linear programming, the dynamic programming, and then we also looked at the multi-objective techniques, multi-objective planning programs, and then went on to the stochastic optimization techniques. Typically, we covered the chance constraint linear programming and the stochastic dynamic programming, and we also looked at the fuzzy optimization, and the specific applications that we dealt with are related to the reservoir operation, multi-reservoir systems, the water quality control. Then towards the end, I have also dealt with the conjunctive use of surface and groundwater, hydropower optimization, crop yield optimization, and today I discussed the interbasin transfer of water, transfer systems where we have large systems. Now, this was a preliminary course on water resource systems. There are several advanced topics. In fact, as I mentioned towards the end of this last application, the problems are extremely complex, and therefore, you cannot put them simply in simple linear programming or simulation models and then say these are the optimal solutions. You need to look at some advanced techniques, and these are some advanced topics that you can consider going through. For example, you may have genetic algorithms, particles form optimization, ant colony optimization, etc. These will provide you with better tools of optimization. Then you have search, you have pattern recognition tools such as artificial neural networks, support vector machines, etc. These you can use it for forecasting of flows, forecasting of the performance, and so on. So, these are some advanced topics that the students can learn. Also, we have some web courses already available on the NPTEL websites. So, you can refer to these web courses. These both are by Professor Nagesh Kumar of IISc. You can just refer to these courses. One is on water resource systems and another is on optimization methods. Both will be of use. In addition, there is a good book on multi-criteria analysis by K. Srinivas Raju and D. Nagesh Kumar. This also gives you a good idea and exposure on several techniques of multi-objective optimization. So, that completes the course portion set out for this course. Before I end the course, I would like to thank NPTEL for this opportunity, and specifically to Deepali Saloke and Guru Prakash for helping me in delivering this course, and to all my students who have taken this course and helped me learn along with them. So, thank you very much, and all the best for you.